In the beginning, not some divine creator, but brilliant human beings were responsible for the steps that transformed the Chinese from a primitive people to a civilization, or so the Chinese creation legends say. In human history, many ancient and splendid civilizations were born and died, and the Chinese civilization is one of them. But China is the only country with uninterrupted human civilization.
Hi there! So this time, we're going to talk about mathematics of one of the oldest civilizations, specifically of the ancient China. So get ready as we will travel back into the past, and be ready as you will learn more about it. So let's get started. Wherein China today is largely a product of its historical past. China is the world's longest continuous civilization. China is one of the oldest civilizations, comparable only to Egypt and Babylonia, which were well versed in mathematics. But unlike these nations, China developed upon her own until modern times.
Since it is impossible to rule an empire as large as or larger than Rome without arithmetic, and given the millennia that Chinese culture developed relatively unimpeded, Chinese mathematics achievements are really intriguing. Now, let's move on to the mathematics of the dynasty that ruled over China from the very beginning. Oh wait, you might be wondering what a dynasty is. So to give you an explanation, it is a succession of rulers from the same family in China. But if a family dies or is overthrown, a new set of family will eventually take power. So now, let's go.
The Xia dynasty was considered as the first dynasty of ancient China. It's generally believed that the Xia dynasty consists of several clans living alongside the Yellow River.
The Xia dynasty is traditionally considered to be the beginning of China's hereditary dynasty, considered mythical by many historians. Xia era relics found in a site called Erletu in the central Yellow River Basin.
Mathematics in China emerged independently by the 11th century BC. Much of Chinese mathematics was developed out of mysticism and astronomy. The earliest inscriptions of numerals can be traced to oracle bone script of the Shang dynasty. The words and numerals of this period were carved on hard media such as animal bones and tortoise shells. Such writing media were then heated until cracked, whereupon the cracks are then interpreted for divination. On these bones, also the first numbers are found. The records of this era provide a glimpse of the decimal system that is prevalent in East Asian languages. However, unlike the positional system used in later eras, there were many symbols for multiples and powers of tens.
About the Zhao reign, we can learn that mathematics is one of the 6 gentlemanly arts, or the Liu Yi. As the book Zhao writes records, the official is to teach the ways to the children of the country, to teach them the 6 gentlemanly arts, the first of which is called the 5 rites, the second is the 6 modes of music, the third is the 5 methods of archery, the fourth is the 5 ways of horsemanship, the fifth is the 6 ways of calligraphy, and the sixth is the 9 calculations of mathematics. From this, we can conclude that mathematics was already being practiced a long time 24 the 9 chapters, but unfortunately, not much is known about the mathematics of that time, since the edict of 213 BC robbed history of her sources.
Though the 9 chapters is considered the oldest of the mathematical works, the first surviving work dealing with mathematics is considered to be Zhou Bai's Wan Jing. Zhou Bai consists of 2 books. The second is treating only calendrical theories, while the first part, however, shows how Chinese could easily work with fractions, and they even knew about the Pythagorean theorem.
Numerology was another form of divination developed in early phases of Chinese civilization. This practice matured during the Zhou dynasty and has survived to the present day. The oldest documentation of numerology in China is attributed to King Wen of Zhou, and this text is called the I Ching, or the Book of Changes. Over the next 3 millennia, the methods prescribed in the I Ching garnered much intellectual intrigue.
There was a pervasive fascination with numbers and mathematical patterns in ancient China, and different numbers were believed to have cosmic significance. In particular, magic squares of numbers where each row, column, and diagonal added up to the same total, were regarded as having great spiritual and religious significance. The Lucius square, an order 3 square where each row, column, and diagonal adds up to 15, is perhaps the earliest of these, dating back to 650 BCE. The legend of Emperor Yu's discovery of the square on the back of a turtle is set as taking place in about 2800 BCE.
Several innovations made mathematics more accessible to the commoner. The oldest decimal multiplication table uncovered from archaeological excavations were compiled around the 4th century BC. This multiplication table was written on bamboo strips, which included the 9 by 9 multiplication table, products with 1/2, and select products up to 90 squared.
One of the most important mathematical innovations of the Zhou dynasty would be the counting board and counting rods. Unique to the Far East, the counting board was the chief computing tool. Numbers were now written using digits that correspond to different place values. This was due to 1K innovation, the decimal positional system. About the origin of these rod numerals, less is known, although there is no doubt they are derived from the counting rods. This, of course, is no proof of the existence of the rod numerals, but it shows the Chinese did have an understanding of the concept of place value, which may mean it was known by then.
The Moheng can be considered a treasured trove of scientific thought native to China. What differentiates the Muhuis from other schools of thought is their attitude towards natural sciences. Many schools of thought only appreciate the utility of scientific knowledge, hence disregarding the need for theory. The Muhuis thinkers investigate the mechanics of nature out of need to understand its fundamental principles. In doing so, the Muhuis were driven to define and explain geometric concepts similar to the definition in Euclid's Elements.
"500 years of feudal wars ended with the ascendance of Qin Shi Huang, the first emperor of China. Qin Shi Huang exploited the best military technologies and a brutally efficient political philosophy to conquer all of China. The legalism of Shangyang, Hanse, and Lacy, with many socio-economic reforms and its uncompromising meritocracy, transformed the Kingdom of Qin from the backwaters of China into an agricultural and industrial powerhouse. He was the man who forged the Chinese identity, but simultaneously regarded as a ruthless tyrant. However, there is little evidence of any mathematical progress during the Qin dynasty. There were probably two reasons. First, the short time span. Second, the immense amount of reform. The Kane dynasty lasted only 15 years. Much of the 15 years was spent on the standardization of writing, weights and measures, roads, and the construction of numerous mega projects. Great building projects such as the Great Wall and the Terracotta Army were built in this era. There was little time for cultivating culture or intellectual curiosity. Furthermore, Qin Shi Huang attempted to destroy much of the antiquated school of thought.
After the fall of Qin, China descended into a civil war between two factions, the Han and Chu. The Han prevailed and ushered a new approach to the unification of China. Unlike the despotism of Qin, which favored efficiency, the Han emperors favored growth and stability. In doing so, the emperors adopted Confucianism as state philosophy with certain legalist characteristics. The Han dynasty was one of the most powerful, prosperous, and one of the most important dynasties in China's history. It existed at the same time as the Roman Empire and was known for starting the Silk Road trade, connecting China with Central Asia and Europe. During the reign of Han Wudi, the Han Empire expanded its borders in all directions, and this expansion in territory opened up trade with foreign kingdoms. It was during the Han Dynasty that Chinese culture began to diffuse throughout continental East Asia and even Central Asia. Culture blossomed for the next 4 centuries and alongside a time to advance mathematics.
In the Han Dynasty, numbers were developed into a place value decimal system and used on a counting board with a set of counting rods called chosan, consisting of only 9 symbols with a blank space on the counting board representing 0.
The greatest contribution of the Han Dynasty mathematician would be the organization of mathematical knowledge. This labor of producing curriculum and word problems was credited to Zhang Kang, the first prime minister of the Han Dynasty.
The Suan Shushu is an ancient Chinese text on mathematics approximately 7,000 characters in length, written on 190 bamboo stripes. It was discovered together with other writings in 1984. The Book of Computations contains many prerequisites of problems that would be expanded upon in the 9 chapters on the mathematical art.
Throughout the entirety of the Han Dynasty, several standardized mathematical texts were compiled. These texts typically include many word problems that involve scenarios relating to commerce, agriculture, surveying, and civil engineering. Zhuozhang's Wanshu, or the 9 chapters on the mathematical art, is considered to be the chief mathematical textbook in the Far East for nearly 2 millennia. The 9 chapters details the types of problems and solutions expected for technical experts and civil servants. The 9 chapters on the mathematical art was one of the most influential of all Chinese mathematical books. Although the author or authors are unknown, they made a major contribution in the Eastern world. It is composed of 246 problems, in which problems are set up with questions immediately followed by answers and procedure. There are no formal mathematical proofs within the text, just a step-by-step procedure. Problems in the 9 chapters on the mathematical art take pi to be equal to 3 in calculating problems related to circles and spheres. There is no explicit formula given within the text for the calculation of pi to be 3, but it is used throughout the problems of both the 9 chapters and the artificer's record. Some Han mathematicians attempted to improve this number, such as Liu Xin, Li Huwi, and Zhou Chongzi, in which Zhou Chongzi later discovered the calculation of pi to be greater than 3.1415926 but lesser than 3.1415927. This calculation would be later discovered in Europe during the 16th century.
Basic arithmetic processes such as addition, subtraction, multiplication, and division were present before the Han Dynasty. The 9 chapters on the mathematical art take these basic operations for granted and simply instruct the reader to perform them. Han mathematicians calculated square and cube roots in a similar manner as division and problems on division and root extraction both occur in chapter 4 of the 9 chapters on the mathematical art.
The Book of Computations is the first known text to solve systems of equations with two unknowns. There are a total of 3 sets of problems within the Book of Computations involving solving problems of equations with a false position method, which again are put into practical terms. Chapter 7 of the 9 chapters on the mathematical art also deals with solving a system of 2 equations with 2 unknowns with a false position method. Chapter 8 of the 9 chapters on the mathematical art deals with solving infinite equations with infinite unknowns. Problems were done on a counting board and included the use of negative numbers as well as fractions. The counting board was effectively a matrix, where the top line is the first variable of one equation and the bottom is the last.
Aside from the organization of Chinese mathematical knowledge, the Han Dynasty made many strides in mathematical thinking. Among the most influential would be the first use of negative numbers. Chinese embraced negative numbers as a very practical construct. One practical example of the extension between positive and negative numbers would be the representation of gains and losses. This acceptance of negative numbers quickly made its way to the use of colored counting rods. In the convention of the time, red counting rods represent positive numbers, while black counting rods represent negative numbers. The use of negative numbers spread westward along the ancient Silk Road, making its way into the India by the 5th century, the Middle East by the 9th century, and the Europe by the 13th century.
In the past, in addition to the ability to write elegant brush pen characters, another required skill for businessmen was to use an abacus skillfully. The earliest known written documentation of the Chinese abacus for swan fan dates back to the Han Dynasty.
After the fall of the Han Dynasty, China did not experience a decline of intellectual development. In fact, mathematical discourse flourished during yet another period of warring kingdoms. Interestingly, it is the era where mathematical theory grew in attempt to understand the underlying principles of the methods prescribed in the Han Dynasty text.
The first period of disunity was the Three Kingdoms, and perhaps the most famous mathematician of ancient China lived during this period. Liu Hui was probably the most creative mathematician of ancient China. He was born not long after the fall of the Han Dynasty. Liu Hui's most influential work was his commentary of the Zhuzhang's Wanshu. He provided better explanations to the old Han algorithms and sought to improve certain geometric formulas. Liu Hui expanded the Zhuzhang's Wanshu by adding an appendix to the text, where he produced more advanced surveying problems using the Zhongqia method. The Zhongqia method was a nascent form of trigonometry which, according to Liu, originated from the Han Dynasty.
The Sunzi Xuanzing is a mathematical text written sometime between the 3rd and 5th century AD by an obscure mathematician, Sunzi. A precise dating of the Sunzi Xuanzing is somewhat difficult. The text makes references of Bodhisattvas and the taxation system issued in 200 AD, suggesting it was written during the Jin dynasty. In terms of mathematical knowledge, the methods discussed in the Sunzi Xuanzing were known since the Han Dynasty.
The Chinese went on to solve far more complex equations using far larger numbers than those outlined in the 9 chapters. Though, they also started to pursue more abstract mathematical problems, although usually couched in rather artificial practical terms, including what was become known as the Chinese remainder theorem. This uses the remainders after dividing an unknown number by a succession of smaller numbers.
Zhu Chengzi and Zhu Ging, a father-son pair belonged to a family of astronomers during the Northern and Southern dynasties. Since the Han Dynasty, calendar making was an active and important area of research. On the practical side, calendars played a crucial role to agricultural productivity and taxation in China. Zhu Chongzi devised a new, more accurate calendar called the Daming Li. This calendar was based on a 391-year cycle which incorporated all his astronomical talents to organize.
In the golden age of Chinese mathematics by the 13th century, there were over 30 prestigious schools of mathematics scattered across China. Perhaps the most brilliant Chinese mathematician of this time was Qin Xiao, a rather violent and corrupt imperial administrator and warrior who explored solutions to quadratic and even cubic equations using a method of repeated approximation. He even extended this technique to solve equations involving number up to the power of 10, which is extraordinarily complex mathematics for its time.